Thank you. Thanks to the organizers for inviting me to this workshop. And today I will be talking about some problems which can be reduced to the determinant and rank of matrices. So let's start with the outline. I'll be going to talk about two problems essentially. One is called disjoint paths, and the other one is just the usual reachability, but in a slightly different setting than usual, which is the dynamic setting. So we'll come to it in a second. So the two fundamentals, there are two very fundamental problems in parallel complexity, so to say, or low-level complexity. One of them is reachability, that is, you're given a directed graph and two vertices S and T, and you want to know whether T is reachable from S or not. And this is complete for the class NL. And the optimization version of this problem, that is, if you want to find length of the shortest path or the shortest path itself, that's also complete for NL. NL is not deterministic log space. I guess all of you know that. The second problem is very similar, but now we are working on graphs which are undirected. So the contrast between directed and undirected graphs means that the problem is complete for the class SL, which was in a celebrated paper proved equal to log space, and so we have these two problems, connectivity and reachability, and in the first part we are going to talk about a variant of connectivity, in the second part we are going to talk about reachability. So the optimization version of connectivity is also NL complete, or at least it's hard for NL, and it is in NL. So coming to the disjoint path problem, what is the problem? So you're given a graph G as usual, and instead of vertices S and T, just S and T, we have K sets of vertices, a set of K vertices, K pairs of vertices rather, Si and Ti, such that we want to know whether there is a path between the corresponding pair from Si to Ti for each I from 1 to K. K is a parameter that can be as big as n, or it can be a constant, depends on the problem flavor that we are going to talk about. So realize that this is distinct from K connectivity. By K connectivity, I mean you are given K vertices as sources and K vertices as sinks, and you want to find out whether there exists K vertex disjoint paths between the two. That is a much simpler problem. And the reachability version is also simpler. On the other hand, for this problem, disjoint path problem, when I say disjoint, by default I mean vertex disjoint. So for the vertex disjoint path problem, is NP complete for directed graphs even for k equal to 2. Even when the number of pairs is just 2, the problem is NP complete. This is for general directed graphs. And for undirected graphs, it is NP complete when K is unbounded. When K is part of the input in binary unary, then it's NP complete. But we do have some algorithms which run for fixed K, which are polynomial time. So the famous Robertson-Seymour graph miner project had at its core this cubic time algorithm for undirected graphs, disjoint paths in undirected graphs, which runs in polynomial time, in cubic time. And special cases of this problem have also been well studied in literature. So today we are going to focus on a very special case. And in a moment we are going to see why this case is even interesting. So the very special case consists of the following. You have the input graph is planar, okay? And all the terminals, that is all the SIs and TIs, lie on a single face. That is, if you see this, so these are the demands. So think of the graph as lying outside this face, and these are the demands. This is SI, this is TI, so this is S1, this is T1, this is S2, this is T2, this is S3, this is T3, and so on. Okay? So, so all terminals lie on a single face, and we want a solution with minimal total length of paths. So the length of paths should be the minimum possible over all solutions where you have k disjoint paths. Correct? So this problem we call, it's called one face min sum disjoint path problem. And let me try to motivate this very special looking problem. So the basic reason to study this problem is because more general problems are known to be intractable, or there is nothing known about them, not much is known about them. So for example, directed general case for even for one face disjoint path problem is NP hard in the plane, and the planar version is NP hard, and it's fixed parameter tractable, though it is fixed parameter tractable in K, that is the number of endpoints, number of terminals. Even in the undirected case, this is open for, NP hardness is open for K is greater than 2. Recently, so while we see that for K greater than 2, it is still open whether the problem is NP hard, recently Bjorken and Husfeld showed that there is a randomized polynomial time algorithm in the undirected case for the two terminal problem. Not necessarily in the plane, in general. And so, which kind of shows how difficult the problem is, that even special cases are quite hard. And we don't know too much about, say, 3dB. On the other hand, if we focus on the planar cases, not too much is known even here. So the two-phase case, when all the forces lie on one face and all the sinks lie on another, that is known to be solvable via our flow algorithm by Dewar, Deer, and Scriber. Similarly, 3dpp is known to be solvable in the one-phase case in polynomial time. Again, notice the dependence on k is very specific, just k equal to 3. Special cases, on the other hand, are somewhat more tractable. For example, the serial configuration, I'll come to the serial configuration later, is solvable in time polynomial in n as well as k, and this is by a very recent paper. So, coming to our results, what we show is that the counting problem for one phase min sum k dpp can be reduced to some constantly empty determinants, which is exponential in k, but still a constant if k is a constant. And not only is the counting problem in, and this is deterministic reduction. On the other hand, finding the witness to the problem, that is finding the k paths, can be done using either polynomial time or it can be done via randomized algorithm which uses the isolation lemma, which we have seen several times in the workshop. So we can also do this sequentially, as I said, in order 4 to the k into omega time, where n to the omega is the matrix multiplication time. So, coming to the proof of these results, or an outline of proof of these results. So let's fix some notation. Let's talk a little bit about the determinant before we move on to more stuff. So let G be a weighted graph on n vertices, say 1 through n, and let A be its weighted adjacency matrix. Further, consider the permutation pi. Then any permutation pi on Sn, on n symbols, can be written as a product of cycles, of disjoint cycles. Just the usual group theory stuff. And the sign of a permutation, that is the number of transpositions in the permutation, can be shown to be equal to so basically the sign can be shown to be equal to minus 1 to the power n plus the number of cycles in the permutation. This is a fact that we are going to use crucially in our algorithm, and we'll see why. C pi is the number of cycles in pi. Let's also define the weight of a permutation to be the product of the matrix entries corresponding to that permutation. So, product of ai comma pi. So now it's easy to see that the determinant is just the signed sum of the weights of these permutations, where the signs come from the sign of the permutation. Correct? This is the usual definition of the determinant. So it can be viewed as a signed sum of weights of cycle covers in G. What is a cycle cover? A cycle cover is a coupling of vertices of G by disjoint cycles. Correct? So it's just a permutation in different guise. And notice that cycles include self loops. There could be self loops, which are just entries on the diagonal, and these are permitted. Okay. So having seen what the determinant is, let's try to apply the determinant to the disjoint path problem. So we will focus on a very special case of the problem, an even more restrictive case than the one we have considered. So this is the so-called parallel case, when all the edges are in parallel. Correct? So conceivably one might have edges in between these which are not parallel, but we don't have those. We are talking about the parallel configuration. And we make a slight modification to this graph. We add edges from Pi to Si inside the face. We subdivide edges at Ri. These are some technical things. Put self loops on all vertices in the graph except the Ri's. Ri's are the subdivision vertices. And put a weight x on each original edge and 1 on the self loops. Correct? So now consider a cycle cover. What is a cycle cover? It consists of cycles which lie outside this. And notice, because there are these subdivision vertices, or there ought to be these subdivision vertices in the middle, they can only be covered by a cycle cover which corresponds to cycles joining, paths joining the corresponding endpoints. So there is a path from 2k to 1 here. I don't know whether you can see the numbers here, but from the source to the terminal, the corresponding sources to terminals, that is the only, those are the only paths possible. One can show that if there is a path from say Si to Tj, then there must exist a crossing of the graph, and that is not possible because these are disjoint cycles in the plane. So with this, we have a bijection between the k shortest paths and cycle covers. So essentially, we can see that if there is no k, if there are no k disjoint paths, then the determinant is 0. There are simply no cycle covers. On the other hand, the bijection between KDPPs and cycle covers preserves the weight of the KDPPs in terms of the exponent of x. Remember, x was the variable that we put on all the actual edges of the graph. The length of the KDPP naturally appears as an exponent here. Correct? And in particular, if we look at all the KDPPs which are the shortest, which correspond to min sum, for which the total length of the paths is minimum, they have the same weight. And what is the weight? It is x to the L, where L is the length of the min sum KDPP. Because it's just the number of edges in KDPP, and that is just L. And and the crucial point is that the sign of all these cycle covers is also the same. Remember, the sign was -1 to the power n plus c pi, where pi is c pi is the number of cycles in the permutation. So what are the number of cycles here? In a minimum sum KDPP, there are k non-trivial cycles here, and n minus m self-loops. Yeah.
So the phase is known. That means
the phase is known.
And the parallel edges or everything is known to the.
Yes. Everything is the phase and the parallel edges are all given, and we want to find out whether there exist k disjoint paths and what is the length of the shortest such convergence. So, yeah. So this is n plus n minus L plus k, and notice that this is independent of the cycle cover. It just depends on L and k, and L and k, L is the length of the minimum sum KDPP, so that is dependent of the particular KDPP we are considering, particular minimum KDPP we are considering, and k is just a parameter for the entire problem. So all the minimum KDPPs have the same sign, which has the good effect that none of these cancel out. None of these terms cancel out, and therefore it counts the smallest degree term. The smallest degree term, the quotient of the smallest degree term, counts the number of min sum KDPPs. So all of them sum up because they have the same sign and they have the same weight, and this weight is lighter than any other cycle cover's weight. So together in the sum, all of them have the same sum, and yeah. Therefore, computing this coefficient is as easy as computing computing this coefficient is as easy as the determinant. Hence, we have reduced the problem to computing the determinant. So this was a very special case, and we can also show that search reduces to counting in polynomial time with this, which is a very standard reduction. You can just sequentially consider the edges and discard any edge such that if you remove the edge, the count is greater than 0. So whenever you do that, the remaining edges form a min weight cycle cover. And search is also in RNC by the isolation lemma. You can just isolate min sum KDPP using isolating weights as exponents of x on the edges E, and discard any edge, removing which doesn't change the min weight exponent. This is the standard way of doing it using isolation lemma. So now we have solved this special case, and we want to solve the general case, general one phase case. And what is the problem with the general case? The problem is that suppose you are given these demands. What are the demands here? The edges inside. There are 4 edges inside, and these are the source sink pairs where we want to find paths between. So, on the other hand, instead of finding the paths between corresponding vertices, we can find larger cycle covers. We can find cycle covers which look like this. There is this large cycle cover which includes 2 demands, and these are so-called spurious cycle covers, and they occur in addition to good ones. So the bijection between required KDPP paths and cycle covers is lost. There is no such bijection, but notice that these spurious cycle covers correspond to a different terminal pairing, for a different pairing of the terminals. For example, we have a path from here to here and a path from here to here. So if the corresponding terminals were paired, we would get the same set of paths. So in particular, if you look at the second picture here, we draw the corresponding pairs which corresponded to paths, the spurious paths, and this covers some of the bad cases that occur here. This covers all the bad cases that occur here. But this creates its own bad cases, its own spurious cases. And these we can again cancel out by another set of new demands. And so we have a recursive procedure which kind of you sum up over all these determinants, and finally you get to the parallel case, which was the base case that we saw. And we need to prove that this process converges. Correct? That we do not get back the same cycle covers again when we express the cycle covers here in terms of cycle covers here and so on. And this is not very easy to do, but still. So we spent a lot of time trying to find the right invariant to measure how to prevent cycles in this, how to prevent circularity in this argument. So what we finally ended up doing was to define a function length which maps demands to actual numbers such that the length of spurious demands is strictly greater than the length of the real demands. And in fact, the length of parallel demands is the maximum. So now we can recursively express a KDPP for a demand as sum of a determinant and KDPP for demands of greater length. And since length is a monotonically increasing function, we get get finally the KDPPs with the maximum length, which are parallel divisions. So here we know how to solve the problem. So we get a signed sum of determinants, whose sum gives us the actual answer. So this is the first part of the talk, and I will now move on to the second part, which consists of dynamic reachability. So for this, I will need to go back to the first slide that I had, which is reachability versus connectivity. And now we are going to talk about reachability in directed graphs. So connectivity. So first, let me say a few words about the model of computation we are going to talk about. So we are going to talk about dynamic complexity. What we are familiar with in the usual case is static complexity. Here, the input graph G is presented in one shot, and the algorithm outputs whether G satisfies a particular property, such as matching or reachability or your favorite property for the graph. And the complexity is measured in terms of your favorite measure of complexity, that is time, space, circuit depth, what of the algorithm. On the other hand, to contrast it with dynamic complexity, here we start out with an empty graph. You're given the empty graph on n vertices, and at every time step, one of three things happens. An edge is inserted into the graph, or an edge is deleted from the graph, or a query is asked. Correct? And what is a query? Is the property satisfied by the current version of the graph? And at every time step, one of these things occurs, as I said. The algorithm input. So now we have to describe how the complexity of this algorithms are measured. The algorithm input consists of the string output at the last step. Every step outputs a string. The algorithm input is the string output at the last step, and the algorithm output is a new string. And the point is, one specific bit must be the answer to the query. So you can use these bits to store intermediate results, and at every step, one of the bits is the answer that you want. And the complexity is very naturally measured in terms of the circuit or descriptive complexity of this algorithm, of this one-step update algorithm. And we can define complexity classes based on these, such as dynamic AC0, where the update circuit is an AC0 circuit, or in terms of descriptive complexity classes like first order. So DINFO is the class where the dynamic class where updates are first order computable. So I will not go into details of DINFO. You can safely ignore it for the purposes of this talk. You can just think of DIN AC0, where all the updates are AC0 updates. DINFO is basically a more uniform version of DIN AC0. Notion of uniformity is further defined. So the main theorem we prove is that reachability is in DIN. Why is this theorem even surprising or relevant or whatever? So it was known for a long time, since the early 90s, that connectivity is in DINFO. This was by a paper of Himaran and Patnaik, who established this area of dynamic complexity and introduced the first couple of problems, which could be a dynamic first order, and dynamic connectivity was one of those. On the other hand, they conjectured that reachability was in dynamic first order, but they couldn't prove it. And the problem was studied in between for several years, and people believed in fact that dynamic first order did not contain reachability. So there were attempts to prove lower bound results for dynamic first order, for reachability in dynamic first order. Somehow we were able to prove that reachability is in dynamic first order by a very simple algorithm. And this is what I'm going to show you now. So the algorithm rests on the rank matrix. So this is in the theme of linear algebraic characterizations of simpler problems. So both NL and UL are much smaller than, so they cannot do linear algebra. And yet, we are translating problems which are related to reachability and connectivity to this class because we can use it to give efficient algorithms. So what is the rank of a matrix? It's just the rank of a matrix. So I will not define it. Our reduction consists of reducing the reachability to rank of a matrix, then showing that the rank is in uniform in AC0, and finally, this is the part that I'm not going to talk about, that dynamic first order is the same as uniform in AC0. So I'm going to focus on the first two steps. So, reducing reachability to rank. How do you use reachability to rank? The approach is to map the graph G to a matrix such that if you have reachability in the graph, then the matrix is full rank. Simultaneously, we want that the matrix should change very slightly with changes in the graph. So if you add or delete an edge, there should be constantly many changes in the matrix P. So now we show how to construct this matrix, and it's very simple to construct. There's nothing great about it. So if you denote the adjacency matrix of G by A, and recall that you can count the number of walks from S to T by just powering the matrix. Correct? So you power the matrix, the adjacency matrix to the higher power, and look at the number of paths from S to T. This is just the STth entry of this resulting matrix. So now look at the inverse of the matrix I minus 1 by n times A, and this is just this infinite sum of powers of matrices. And you can prove this because it's invertible. Why is it invertible? Because this is a diagonally dominant matrix and it is invertible. Therefore, you can even just multiply out both the sides by I minus A by n and verify that the sign is identical.